Hello, everybody. Welcome to the quantum tutorial from Argonne National Laboratory. Today, this is going to be interesting tutorial. What we decided is to split it in 5 days. Every day, a weekday, we're going to have a presentation for 1 hour, and it will be followed by a hands-on session for 1 hour. And yes, and if you are not a speaker, please mute yourself. And please disable video as well. And every weekday, we're going to have a presentation for 1 hour, and it will follow by hands-on session where you'll be able to ask any questions you have. During the session, I will collect the questions. Please type them in the chat window. We'll collect them and we'll answer them at the end of the session. But during Qiskit session, please unmute yourself, ask yourself. It is supposed to be a very interactive session. And as you can see, each weekday you'll have presentation. On today is going to be about Qiskit by Kevin, who's a talented student from University of Chicago. And we have our presentations from on Tuesday, Wednesday, Thursday, and Friday. You have seen the agenda. The sessions, the presentations will be recorded and hands-on as well. After that, we'll edit them and we'll add them to Argonne's YouTube channel. If you're not wishing to be recorded, feel free to leave, but I believe everybody's signed a consent. And that's all on my side. I'm going to stop sharing. Kevin, now please try to share your screen.
Right, so thanks for introductions. Let me try to share my screen. Hopefully it works. Okay, let me begin. So as you mentioned, today's session is going to be a sort of an elementary one. So if you have any questions or if you think I'm going too fast, feel free to raise your hands, or if you can just ask me anything if you want. And then I believe someone will pick it up the answers once you have it, and then I can just stop and have your questions. This will be a very interactive one. Right, so today's topic is going to be first a little bit introduction to quantum computing, and then some hands-on experience on Qiskit. So my name is Kevin. I'm currently I'm currently a rising fourth-year PhD at University of Chicago. I work on quantum computing both on the hardware side and then the software side. Okay, so first is a little bit a touch on what can Qiskit do. So Qiskit is sort of like a integrated software package made by IBM that can help you build on enjoy all these sort of quantum computing experience. So to put it into more details, and then there are in general roughly, and then it's not an exact definition, roughly 4 different kind of areas you can do. So first, you can sort of do these elementary buildings and testing your own quantum circuits. And then secondly, you can simulate whatever the quantum circuits you've built via possible computers. And say you can either do a noise-free version, saying that basically there's no quantum noise and can just see what the circuits are supposed to do, or you can also customize your noise and then add your noise into the system. And thirdly, you can also try to execute your quantum circuits on hardwares. So IBM has these and their own built-in superconducting circuits for you to run, and then recently, they've also paired together with these ion trap companies, so that I can also execute their code on atom traps via Qiskit. And lastly, you'll also have access to a collection of quantum algorithms such as optimization and then quantum finance, quantum machine learning, or quantum chemistry, etc. Right, and then so for today's talk, we're gonna focus more on the first two parts. Basically, I will teach you guys how to build a quantum circuits on Qiskit, and then try to simulate some quantum circuits on a classical computer with noise and without noise. So this is sort of like a mini agenda of what we're going to talk about today, and then the first will be an introduction or sort of a crash course of quantum computing. So I will introduce what are qubits, and then what are quantum gates, and what are quantum meshes. So these three are the sort of the building blocks of quantum computing, especially digital quantum computing. And then secondly, I will walk you guys through just get hands-on of how do you build these elementary quantum circuits and quantum gates. And lastly, I will provide some interesting quantum algorithm demonstration, say including quantum teleportation and then also a global research. And then you can also look at the Qiskit textbook because most of the things in here is going to be included in the Qiskit textbook. So feel free to reach out there, and then they have a much more detailed explanations than what I have today. Okay, so first part is going to be quantum computing, sort of quantum computing 101. Yeah, and then so this is sort of a nice picture I copied from IBM. So actually it was originally titled as quantum computing in a nutshell. So this way is sort of give you a way to visualize how quantum computing is done via quantum interference. So the idea is sort of saying, in the first place, you are trying to create a superposition of all possibility of quantum states. And then you do these various, these are called quantum gates or quantum circuits. And then you're trying to use interference to cancel out on all these unwanted results and in the middle steps. And lastly, you arrive at a particular quantum solutions. I mean, it can be multiple quantum solutions, right? And sort of then reside in here. And you'll perform measurements to sort of get your precise result and all that stuff. So other than using quantum interference, you can also, there's also another interesting phenomenon called quantum entanglement. And this is also very useful in quantum computing, quantum communication, etc. So I will get into details about more of these. But this is just a rough idea of saying basically how quantum computings are performed. All right. So with that, let me first introduce the basic building block of quantum computing, which is qubits. Okay, so the picture on the left sort of gives you a nice comparison of the difference between a classical bits, which is the bits our typical computers are using nowadays, and then versus the qubits, which are on a quantum computer. So for simple classical bits, you can only have a discrete values between zeros and ones. Saying like sometimes you can have a higher voltage to be on 0 and then a lower voltage to be 1, or vice versa, depends on how defines it. And then for qubits, you'll typically have a two-level systems that will show you which zeros and ones are. And then one interesting thing is that your qubit states can stay in the middle, which is called the superposition state between zeros and ones. And then, in fact, these superposition state can be any linear combinations between the orthonormal basis, which is the zeros and ones. So you can have some wave function, which is your qubit states, and be a combination of alpha 0 plus beta 1. And then you have this normalization condition that alpha squared plus beta squared equals 1. So this is for a one qubit systems description, and you can also generalize this to a multi-qubit system. So you can just simply do a tensor products between different qubits. Say like if I have two qubits both in a 0 state, I'll have a 0 tensor 0 equals 0 0 state. written here. And then if I have the first qubit in the 1 state and the second qubit in a 0 state, I'll have a 1-0 state for a 2-qubit system. All right. So more formally, you can sort of visualize the qubits onto a Bloch sphere. The Bloch sphere is sort of a virtual spheres are created by physicists in general. So this will tells you say if I have a wave function psi equals alpha 0 plus beta 1, and then if I parameterize as alpha equals the cosine theta over 2, so I will see the state angle is in here, which is the how far my psi is away from the z-axis. And then if I also express beta as e to the I5 times sine to theta 2, and then this phi is sort of my phase, basically how much I'm away from my from the plane perpendicular to the an xz plane, right? So with this, I can sort of convert whatever is on the sphere onto the quantum state parameterized by alpha beta, or namely theta and then phi in here. Okay. So typically people generally express quantum states as vectors once they're doing quantum computing. So for a 0 state, I will have a 1-0 vector, and then for a 1 state, I will have a 0-1 state, 0-1 vector. And then for any arbitrary alpha 0 plus beta 1, I'll just have a vector that looks like alpha and beta in here. So on the left is the single qubits, and then on the right is the multi-qubit systems. We can say for a 0 state, which is the qubit 1 being in 0 and qubit 2 being in 0. So I can simply do a tensor products. I will express my 0 state as this 1/4 vector. And then for a 1-1 state, I will also express it as 0-1 tensor 0-1. And then we'll have a 0-0-0-1 vector. And then you can sort of generalize to be, say, if you have 0 times O times 1, you'll have 0-1 and tensor 1-0 in here. All right. And then next, following the vectors for the qubits and qubit states, now we have matrices for quantum gates. So in general, for any 1 qubit gates, these are generally expressed by a 2x2 matrix. Say we have these things called the X gate and then Z gate. So if you're a physicist, you know this is sort of basically equivalent to the sigma X and sigma Z operators. And then basically sigma X is 0, 1, 1, 0. And then sort of in the computer languages, it basically means that you are flipping the up A and B in here. Say if my original gate, original quantum state is in A0 plus B1, now will be B0 times plus A1, right? So basically, you can just multiply out this element-wise, and you get a reverse gate. So this is sort of point as a NOT gate, and basically you're flipping these states between the 2 level systems in the quantum computer. And again, you can also do this another interesting gate called hammer gates. Basically, you're moving a basic state into a superposition state. Say if you are doing hammers on a 0 state, you will accompany something called the plus state, which is the square root 2 of 0 plus 1. And then if you do hammers on the 1 state, you'll have a minus state, which is basically 0 minus 1 times 1 over square root 2. And then similarly, if you do a hammers on the plus and minus states, you'll negate it back into 0 and 1 state. Other than single qubit gates, there's also another very important gate called multi-qubit gates. And then, for instance, typically people will have this thing called control X gate or C0 gate. basically you are trying to perform a XOR operations between the control and the target bits. This is your 4x4 matrix. So typically, this will act on a on a 4x1 vector, basically a 2-qubit space. And so sort of the truth table is sort of shown here. So if your control bits is 0, then don't do anything on target bits. Say 0, 0 becomes 0, 0, and 0, 1 becomes 0, 1. So basically, it stays the same. And then if your control bits is in 1, then you flip the states of the second bit, saying now it transformed the 1, 0 state into the 1, 1 state. So second qubit is flipped. And then similarly, for the 1, 1 state, this will flip the second qubits into the 1, 0 state. So you can sort of saying this is actually a modulo 2 operations. So 1 plus 0 modulo 2 will equals 1, and then 1 plus 1 modulo 2 will equal 0. So yeah, so in the computer science language, this is an XOR operation, a control the X operation, right? So with this, the last part in the quantum circuit is this thing called quantum measurements. So one annoying thing for quantum computing is that once you have computed whatever's in your quantum circuits, you will have to extract information, because typically there will be a superposition or some entangled states in between everything. It's not unlike classical computers, you can just directly get the results. In the quantum computers, you'll have to perform the measurements in order to sort of extract your observables to see what are actually happening. And then from the observables, you can predict what can be the possible superposition of quantum states in your previous circuit computation. So this is sort of the formal definition of, say, if I want to find the probability of measuring some states psi in the state X. So my state X is my basis. So basically, I'm measuring my state psi in the basis X. So the probability of getting an X state, the X state for this is it can do a Bloch times cat, and then do the square root of it. Say if I have example, I have a Q0 state equals 1 over square root of 2 times 0 plus I divided by square root of 2, 1. So I first do a broadcast of this. Say if I want to know, I want to measure my state Q0 under the 0 basis, right? So I'll just first do the broadcast, and then I will expand it out on both part of this, the multiplication rules. So I'll have 1 over square root of 2 bra 0 times cat 0 plus I divided by square root of 2 bra 0 times cat 1. So and the bra 0 times cat 0, basically these two, because they're on the same basis, I know this amount will amount to 1. And then for 0 times 1, these two are orthogonal, so basically, if you follow them states, you will end up with a zero amount in here. So adding them together and then square it, I know that for this particular state, I will have a 50% or 1 over 2 probability of measuring this state in the 0 basis. And then you can also verify this, saying you can do the same thing for the 1 basis. You also get another 50%. Okay, and then so similarly, this also applies to multi-qubit systems. You can measure each qubit separately, most of the times. All right. So now let's try to combine all these 3 parts together and then see what things look like. Right. So this is a sort of a typical quantum circuit example. And then, so in the beginning, you will initialize your 5-qubit system. Like, I mean, it can be any number of qubits, but here, example shows it's a 5-qubit. Right? And then you can, you'll also initialize the corresponding Qiskit bits for you to record the measurement results. Because, in a quantum stage, you have to extract information and report it on the Qiskit bits. And then after you have initialized your qubits, you will perform a series of quantum gates. So you can have some Hadamard's gate in here and the X gate. And then, for instance, these are the control NOT gates. Velocity before some Hadamard's in here. And then the last step is your quantum measurements. So you will measure, for this case, you will measure the first 4 qubits and then record it on the 4 Qiskit bits. So typically they are in Z-basis measurements, so meaning you are measuring the Z observable, which is the sigma Z operator. And then sometimes you can also do X measurements or Y measurements, or depending on the particular quantum computers you're at. But for the IBM Q system, typically you're doing Z-basis measurements. Right? And then, so for each lines, basically are saying, you can sort of think them as proceeding by time. So, say for qubit 0, I'm first doing a Hadamard case in the first place. Then I wait till some period of time, and lastly, I do a Hadamard case in the end, and then I perform the measurements. So, like similarly, for Q1 qubits, and I will do a first Hadamard, and then I will do a control NOT operations. Basically, Q1 serves as the control bits, and then targeting on the qubit Q4. And then lastly, on Q1, we'll do a Hadamard, and then followed by the measurement. Okay, so if there are no questions, so now is the time to play with some basic Qiskit operations. So once you have downloaded the file, you can try to navigate your file into this page. So you can try to open this notebook called basics.ipython notebook. So this will look like this once you have it. All right. So since these quantum codes are built on sort of these things called IPython notebook, so very simple execution you can do is that you can click on the run button, saying like so first I will do some imports from the Qiskit libraries in order for me to call these quantum methods. So I can just click on run, and then typically it will take seconds to import all these statements. So this should be fairly easy. And then the first part is that let's try to build initialize a quantum circuit objects. So first you can sort of say, I can define the number of qubits I'll have in my quantum circuits, saying for this case, I will have a number of quantum bits equals 2. So I will name this as this variable, and then I will create a circuit objects that is that is a quantum circuit objects, and then parameterized by this number of qubits parameter. And lastly, I do circuit.draw to sort of visualize what my current circuit is. Okay, so if I execute this, this will look like that. And then basically you'll have 2 qubits, Q. So these quantum computers are typically index, a 0 index. So the first qubit is called Q0, the second qubit is called Q1. So if I change that to some other parameters, now you can say I have 1 qubit, so this will just be a simple qubit in here. So if I do 3, so now I will have 3 qubits. And then, vice versa, if I can do 4, now I will have initialized a 4-qubit quantum circuits in here. Okay. So with this, let's try to add some interesting quantum gates. And then now, basically, let's execute this again. And then first, again, you still have to define your quantum circuits and then parameterize by the quantum gates, by a number of qubits. And then slowly you begin to add this quantum bits. So maybe I can start with here. Simpler. Right, so like in the first place, I only add an X operator, meaning the X gate. So and the way you can do gate is that you can just call circuit.x, meaning that you are adding an X gate in here, and then you can add some barriers, sort of separate out the gates between each other to make sure they don't, cross the lines, right? And then now I'm adding the X gate in the first qubit, which is actually qubit 0, right? So then the X gate parameters is here, right? So when 0 meaning I'm doing X gate on qubit 0. So if I make this 1, then this X gate will land on the qubit number 1, and the Q1, which is the second qubit. Right. So now if I do X parameterized by 1, then I will do X gate on Q1. Right. And then so similarly, you can also do a sequence of gates and then say, let me do Y on 1 and then Z on 1, and I can do some RZ, which is the rotation along the Z axis, and then I can do another control knot and then some control Y gates. So this is in the end looks like this. So first I'll do an X gate and a Y gate, then Z gate, then I do an RZ gate, and then lastly the CX gate followed by a CY gate. Okay. So once you have that, another interesting property is that typically a lot of times you can see quantum gates can be parallelized. So if I don't add the barriers to separate out the gates, I can sort of draw things together. That looks like this. Yeah. So the first X gate acting on qubit 0 can be parallelized with the Y gate acting on qubit 1. And then the control gates cannot be parallelized because they occupy all the qubit space. Okay, so with this, let's lastly do the quantum measurements. Saying quantum measurement is built on this method, so we can call them circuit.measure all. So now we're recording all the quantum qubit information onto the two classical bits. Basically, this is sort of your measurement symbol. So I'm recording wherever I measured from qubit 0 onto the first classical bit, which is in classical bit 0, and then I'm recording my information from Q0, which is second qubits, on my first on my second classical bits in here. Right. So with this, let's try to do some interesting quantum state. So in this case, we'll try to create this spell state, which is, for physicists, this probably is the entanglement state. So this state is sort of expressed out as the 0, 0 plus 1, 1 divided by 1 over square root 2. So let's sort of, understand this from the math perspectives. So, in the beginning, you will have initialized your quantum bits to both zeros in general. And then the first step you do is that you will apply the Hadamard on qubit 0. So, if you can recall, the Hadamard operation is in here. So it will change the 0 state into the plus state. So the 0 state will become the 0 plus 1 divided by square root of 2. So once we get back in here, so if I have a 0 state, my first 0 state will become 0 plus 1 divided by square root of 2, and then tensor together with my second state. So once you expand this tensor products out, you will get a 0, 0 plus 1, 0 divided by square root of 2. And then after the Hadamard, I will perform another C0, which is saying if my first qubit is 0, I don't do anything to second bits. If my first bit is 1, I will flip the bits for second bits. So for this case, my first 0 state, I won't do anything because my control bit is 0. And for second state 1, 0, I will flip the second bits from 0 to 1 because my first bit is 1. So after the C0, I will get my Bell state, which is 0, 0 plus 1, 1 divided by square root of 2. Okay, so let's see how this process is done on a quantum computer. So, so I will define my circuit called Bell state circuit. So this is parameterized by the 2 because I will need 2 qubits. I have a quantum circuit object parameterized by 2. And then I will do a Hadamard, which is Bell state circuits .h. So this is Hadamard acting on qubit number 0. And then I will do a Bell state circuit dot control not, which is the CX gate. And then so I'm controlling on the 0 qubit, targeting on the first qubit. And lastly, I do measure mall, and then I draw it. So this will be the circuits I'm creating the Bell state. Right, so with all of this information, let's try to perform the quantum measurement to see if the state indeed we're getting is the Bell state in here. Right, so to sort of do things on the quantum machines, you can, like in this demonstration, I'll first want to run things on the quantum computer simulator, which is, a simulator that tries to mimic the perfect quantum computer, meaning that there are no physical noise, and that affects the quantum computation. And then this sort of means that all these quantum gates and then measurements have no error, but in a real case, there will be errors on the quantum gates, and then there will also be the error called spam error, which is sort of simplified as the initialization and then the measurement errors. And the other assumption is that there are no restrictions on the multi-qubit connectivity, meaning that you can do the multi-qubit gates between any pairs of qubits or any groups of qubits if there are more than one controls. But like in the real case, that is in general not true, especially in the superconducting systems, because typically their connectivity is only nearest neighbors. Yeah, but for now, let's forget about that and then try to assume that we have a perfect quantum computer or to simulate. Number 6. Okay, yeah, so sure. Okay, so again, so let's first define a quantum circuit objects for us to store all these quantum gates and measurements, right? So we name them as a Bell state circuits, and then we first create a quantum circuits on our 2 qubits. So now we'll have Q0 and Q1, right? So like after I initialize my qubits, I will first add a Hadamard on qubit 0, right? So this is called, in this case, Bell circuit.h. You're calling the h, which is the Hadamard methods. You're applying the Hadamard gates exactly on qubit 0, right? So that is a parameter. And then after the Hadamards, I'm doing a C0 gate or a CX gate. Basically, we call the circuit .cx, and then the first parameter is where your control bits is landing at. So the first parameter will tell you I'm controlling on qubit 0, and the second parameter will tell me what my target is. So 1 means I'm targeting on qubit 1. So this CX01 will be this part. And lastly, I do measure all, meaning that I'm doing the quantum measurements for both Q0 and Q1, and then I record the measurement results on the classical bits. Right? Okay, so and lastly, I draw them to sort of visualize, to sort of give you this plot. Okay, so yeah, and then Alan has a question: how to customize gates? For instance, evolution generated by certain Hamiltonian. Okay, so I believe and this operation can be how to put this so the customize the gates by the Hamiltonian is not elementary because like I think in general these gates are set by its own Hamiltonian, and then for instance if you want to run these the actual control knot gates on the superconducting circuits, they have a built-in, say, James Conway models or maybe some, circuit QED models, and then that are in general not customizable. But like, there might be some tools you can try to customize the, say, the pulse sequence or how the measurements are performed by a certain by a certain range of Hamiltonian, but like maybe not all. Yeah, so I don't think the Qiskit is as flexible as Q-tip. I think in Q-tip you can sort of plot everything you want, but like in Qiskit in general these are not very easily customized. Alright, so with the quantum circuits in mind, we can try to execute the circuits on the quantum machines. So first, we can try to define this thing called the Kasim simulator. So Kasim simulator is a classical simulator that tries to mimic the behaviors of quantum machines, right? So this Kasim simulator is located in AER. So AER is one components in Qiskit. So you can do an AER dot get backend, meaning that I'm trying to specify my backends to be the Kasim simulator, and then I call this backends as the backend sim, and then so this is now my sort of simulator I can call, right? So to sort of simulate these experiments, I will call another method called execute. And in execute, I will specify which quantum circuits I want to execute it on, and then which backends, or meaning like in this case, I will execute this on the Kasim simulator backends, and I have to define how many shots I have. Right. So together, we will get a job in this end. And then after I get the jobs, I can call job.sim.result. And so this will collect me the simulated results I can have. And then inside the result sim, I can try to extract the counts from this. Right, so let's try to execute this again. Okay, let me try to define the pulse circuit. Again. All right, so in this sort of count regime, I can see that inside these 1,000 shots, I get 506 shots that tells me it's 1-1 state, and then I get another 494 shots I get from 0 state. And then we can also visualize this to be in this case. So like, since all quantum measurements are probabilistic, so every time you execute these circuits, even if you have a final state output is the same, and then your measurements will sometimes give you some variations in here, right? So for this time, I guess some more states clustered in the 0 state, and then some more states in the smaller states in the 1-1 state. But like, once you execute multiple times, you can sort of see then they are roughly 50-50%. So this measurement result will correspond exactly as my Bell state in here, right? Which is exactly 50% 0 state and then 50% 1-1 state. Right. So in general, you will want your shots to be big because, like, say, once I have, if I set my shots equals 10 shots only, say now. Let's see what we get. Yeah, so now I got like 40% 0, 0 and 60% 1, 1. So this can be very misleading. I can just say, well, and this is not exactly 1/2, right? And this time is perfect. But like it's only a lot. And if I do it again, it'll be 4, 4, 6 again, and then this time will be 6, 4, and then sometimes you'll even get 7, 7, 3 or 8, 2-ish. Right. So like in general, when you're executing quantum algorithms, you generally want to set your shots to be some big numbers so that you can sort of better extract whatever the end quantum state you have. Right. So with the perfect simulation above, let's try to do some noisy simulations. So in order to have these noisy simulations, let's try to call a thing called a fake backend, saying that this backend is still operated by the classical simulator, classical computer, in the sense that it will try to mimic the noise behaviors of the actual quantum computer. So in this case, we will import this thing called fake Vigo. So Vigo is actually a real machine. The fake Vigo is a simulator that tries to mimic the behavior of the Vigo machine. So we can try to see the configurations of the Vigo by just calling the backend in line 35 in here. Okay, so like you can sort of see that there are 5 qubits in this case, and then and each vertices starting from 0, 1, 2, 3, 4 are the qubits. And then the edges between the vertices are the connectivity, meaning that, say, I have a line between qubit 0 and 1, meaning that it can perform a CNOT operation or CZ operations between 0 and 1. And then 1, 2, meaning that I can do anything between 1, 2. See, there's no edges between 0 and 2, right? So this will mean that it cannot do any CNOT or CZs between 0 and 2. So this is, as I mentioned, the connectivity is an issue. And in typical superconducting circuit cases, they can only be nearest neighbor connections. Okay, so this is the number of qubits in the case. Quantum volume is something came up by IBM. It's sort of to roughly estimate how powerful your quantum computer is, basically how much quantum computing you can do. And then there are also some allowed maximum number of shots. And then, so the next show, you can click on this slide, will show you the sort of these physical properties. And then the first column is the frequency. This is the Rabi rays. You can sort of oscillate between, physically, you can oscillate between these sort of, what I call this, the anharmonic two-level systems. And then say between, this will be your the Rabi frequency that oscillates between the zeros and ones. And then the T1, T2 are these sort of the decoherence errors. T1 is like in general like the expectation time how much it will decay from the excited states to the ground state. And T2 is sort of these dephasing errors. Basically, once you're series in the equator, you can sort of your phase will propagate along the equator. And then these numbers are the single qubit errors, right? Say if I perform an X gate in here, I will have a say 0.04% of getting it wrong. And lastly, is my readout errors, and then for each readout, I will have a 7% of chance of getting it wrong. So these readout actually one of the major contribution of the errors. So this is say if I measure them 10 times, I will have one time I will get it wrong. So this is kind of a serious problem for the current stage. Right, so this is another error source which is called the multi-qubit errors. And then for this is that they are trying to perform a thing called randomized benchmarking, meaning that you are trying to perform a sequence of arbitrary gates between these pair of qubits, saying they are doing control knot between 3 and 4. So in this case, the average gate error rates will be 0.7%. mean that, say, like for 100 execution of C naught, I will get one of them as a wrong one. So the multi-qubit gates error are also kind of the majority of the errors as compared to the single qubit errors. Right, so this is sort of the error mappings between all qubits. So once you see a sort of a darker color, mean that your error is greater in these pairs, and a lighter color mean that your error is less. Here, yeah. So yeah, this is something you can sort of toggle between. And for this backend slideshow. Okay, so now comes the final time. Now we can try to simulate the Bell-state creation circuits under this machine, right? So now let's do the same code around here, and then do this. Okay, so we can sort of see that the majority of 1 will still be located as the 0, 0, and 1 state, but unfortunately, the errors will cause the quantum states to sometimes locate it under the 0, 1, and 1, 0 state. If we execute them again, this will be probably some similar rates in here. Do it again. So in general, you'll kind of see that the 1, 1 state is most of the times smaller than the 0, 0 state, because in theory that should be the same, but in reality it's not the same, because in general the 1 states are encoded on the excited states, and the 0 state are encoded on the ground state. So the excited state will tend to decohere to the ground state. So most of the times on the real machines you'll see the 1, 1 states will be a little bit smaller than the 0, 0 state in this case. Let's try to ahead with the last part of this section, which is let's try to see some restrictions on the multi-qubit gate connectivity. Say for this case now, if I wanted to do a C0 gate between 0 and 4, right? So this is my abstract quantum gates as are trying to do a control on Q0 and then targeting on Q4. But once you are trying to look at the actual configuration maps, there are no connectivity between 0 and 4. And how do we do this? And there's still a way to do this, which is called swap gates. Okay, so let's now try to do this thing called transpile. So this transpile method is trying to map your abstract quantum circuits onto the real physical hardware. That is, let's see. My circuit does this, and then I run them saying so in this case, my transpiler it will build these swap operations between qubit 0 and 1, and then qubit 3 and 4. So going back to the configuration here, I now swap my qubit 0 with 1, and then swap my qubit 4 with 3. So in that case, that will allows me to have a connection between 1 and 3, right? So that's what will allow me to sort of do these C0 operations between 1 and 3, which is originally not feasible because 0, 4 are not connected. Okay, so you can sort of see these swaps operations in here, and then also operations in here, and then they can be done under 3 C0s. And you can sort of work out the math, and 3 C0s actually clustered together equals a swap operation. Okay, and then there's also another case where sometimes gates are not native to the superconducting circuits. For instance, I'm trying to do this thing called the total volley gates, meaning that I'm doing double control on the qubit 0, Q0, and Q1, and targeting on Q2. So this is my abstract quantum circuits. Once I'm trying to map to the actual quantum machines, it's going to be more complicated. So this time we are calling another backend that has full connectivity between a cluster of 3 qubits. So this time the backend is called fake Yorktown. So you can sort of visualize now. And then this have sometimes a better connectivity than the previous Vigo machines we have. Since this is only there's no a group of three that are fully connected, but in this case we have a group of three connected qubits. So now let's transpile this circuits which are trying to do the topology gates, and then this will look like this. Basically, sort of translating that you will need at least 6 CNOS for you to perform these multi-qubit topology gates. So this is sort of the transpile circuits you have here, and then this is sort of equivalent to the general textbook and topology gates once you have visualized in here. And then there are some differences with the same qubit gates because due to some imperfections of the optimizer in the Qiskit. In general, they're equivalent to each other. Today we'll do the first one is called quantum teleportation. Okay. So the general idea is that they have two person. Name is Alice and Bob, right? So so Alice wants to send quantum information to Bob. Say, for instance, he wants to send the qubit state, say psi equals alpha 0 times beta 1 to Bob. And then so she can do this, sometimes in long distance via these two Qiskit and then entanglement and qubit pairs. So Alice can transfer or aka teleport her state psi to Bob. And then this teleportation can happen in long distance. And I believe I think this teleportation was verified by some experimental groups under many kilometers between. Right? So this is there are some great experimental works on this before. Okay, so these are generally can be done in like 3 steps. So the first step is that I will first create entanglement pairs, and which is as demonstrated as before our the quantum circuits to create the entanglement by doing like Hadamard plus T0, or there are also other entanglement generation methods from the physics basis side. And then second step is that Alice performs some operations on her qubits, and then she will send the measurement results on her bits to Bob over a classical communication channel. So this sort of it's not like a complete teleportation because you will still need a classical channel to send a classical information from Alice to Bob. In order for Bob to perform some follow-up operations based on whatever the classical information Alice sent. And so I wouldn't entirely call this absolute quantum teleportation, but somewhat like a sort of a halfway quantum teleportation. Because you will always need these quantum channels and then the entanglement pairs created before she makes that communication. Okay, so this is sort of the example of the quantum circuits for quantum teleportation. And then so these are basically initialized to have 3 quantum bits and then 2 classical bits. And so the qubit 0 and qubit 1 are Alice qubits, and then qubit 2 is Bob's qubit. So Alice will try to create some arbitrary quantum states in the beginning, and the second part, I'm sort of separated by barriers, now it's easier for you to see, is the created entanglement pairs. So this is the hammer plus the chronot. So if Alice wanted to do this with Bob, saying like one way she can do is that if Alice and Bob are both on the same spot on Earth, so Alice and Bob can create this entanglement beforehand, and then Alice can shoot herself onto a satellite, or Bob can shoot himself onto a satellite, and then Alice can perform the future operations afterwards. Right? So these operations has to be created beforehand. This entanglement operation. Okay. And lastly, Alice measured some of the output from her end, and then she stored her measurement outputs onto the classical bits. And then now she lastly sent this to classical information to Bob. And then Bob will perform some corresponding operations. So after these sort of classical post-processing via Alice classical information, then after this end, in the qubit 2, which is Bob's qubit, so Bob theoretically has the original quantum states given by Alice, which is in the purple one in here. Okay, yeah. So with that in mind, let's go to the song session. All right. So first we'll do some sort of import statements in here. Okay. So now let's try to create a arbitrary one qubit state. Say now I call this psi equals a random state, partners with one saying I want a 1 qubit version arbitrary state. So now my state will look at this about Bloch Sphere, and then this is my vector array. So if I run execute again, it will give me some other random states that will locate it at a different position on the Bloch Sphere. So let's just try to do this for now. Okay. And then with this arbitrary states, we can initialize our quantum circuits with this arbitrary state, which is called the initialize state. And then you can just call this initialize methods based on the arbitrary state we created before. Okay, and then now after I create the initialization gate, I can do another setups of the quantum of the place I can place my qubits. So in this time, I initialize things by calling the quantum register and then the classical register, because it's easier for me to name things in the later parts. So then I initialize a 3-qubit quantum machine and then 2 separate classical bits around here. And then I assemble together the quantum bits and the classical bits again by calling the quantum circuits up. Yeah, so now once I have this, it's going to look like this. So again, I will have 3 quantum bits. The first 2 quantum bits are owned by Alice, and the last bit is owned by Bob. And then there are some classical bits afterwards. Okay, so let's now continue to step 1. And so first, what we'll do is that we need this Talmon person to create a bell pair between the Alice and Bob. Right? So simply do a header mark and a control out operation. Let's switchwise this again by the same code. Now I have my original Alice state, arbitrary Alice state, and the Talmon will give the entanglement pairs between Alice and Bob. Okay, so yeah, step 2 is Alice will perform some operations after this. So this will now be Alice's operations. So these operations can be performed in anywhere as Alice wanted. So Alice can just send herself to a satellite or send herself to Mars and still perform these operations, and that will still work. But this part has to be created before. But this part can be done anywhere she wants. Right. So with this, now we can say Alice will tend to measure whatever the outputs she has, and then send this output information to Bob, and then via a classical channel. So this double line means a classical channel. And then lastly, Bob, which was at the qubits in 2, then he will do these classical control operations based on the information he received from Alice. So if he received 0, information from Alice, he will do a X gate. He won't do anything. And then if he received the 0, 1 state from Alice, he will do an X gate, and vice versa. If the 1, 0 is received, he will do a Z gate. If 1 is received, he will do a ZX gate. So now let's define Bob's classical control. So the classical control is kind of being defined in here. So the classical control is that you can do an X gate on the quantum circuits if the condition is met. Right? Say if my original bit is 0 and don't do anything. If my original bit is 1 and do an X. So similarly with the Z gate here. Okay, now let's assemble things together. Now my state, my entire quantum circuit looks like this. So this is basically the same circuits separate mentioned in here. All right. So okay. So one way to see the actual output is by a thing called the state vector simulator. So state vector simulator will sort of try to output all the everything in the original vector form, right? So then if I say now I call the get backends and then specify them to be the state vector simulator instead of the previous custom simulator, now my backends will be the state vector simulator. Then I run this, and then I get the actual final state vector from this, and then let's try to see this. And then we get something in here, which is my qubit 0 and qubit 1 are the Alice states after the measurements. And then it's a sort of, of course, and it's the clock state after the quantum measurements. As someone mentioned, once you're performing the measurements, your bits will always collapse to basic state and from the measurement observable. And then this qubits will store Bob's information, which is it's called teleport information. So now let's try to compare this states with the original Alice states in here that we initialize. Yeah, so we can see this is the exact state that Alice created. Now this state has been successfully teleported to Bob's location, which in here. Which means finally our job is complete. So very good. And we now Bob has the Alice state, and he wants it. Dive a little bit into the math behind why this circuit makes sense, right? Why is it giving us the correct outputs teleported from Alice?
There is just another question just pop up.
Do you need to run many shots? So that's an interesting question because in this simulation experiments, I don't do any shots because I'm simulating under the state vector simulator, right? So this state vector simulator will output me the exact quantum states being there without doing any shots in between. So in the actual quantum teleportation experiments, you will need to do many shots in there. Because it depends on what your machines is set up, because like in this case you can sort of design your own machines that perform something other than Z basis measurements. And then it being sort of tailored towards your specific quantum encryption protocols you want to have, right? So so that actually will be a good question to ask like some experimental groups such as David Oshlum's or Andrew Cleveland. So I'm not an expert of that, but in the real experiments it might be a little bit different than the actual and the general quantum computing circuits. All right, so here is sort of a general walkthrough about the math. Say again, this is our pre-created entanglement pairs between Alice's second qubit and Bob's qubit, right? So now I will put these entanglements in pairs together, tensor together with my origin state, which is the alpha 0 plus beta 1. And then if you do the tensor product and expand it out, this will look like this. So some sort of a 3 qubit states. So for step 2, now Alice wanted to apply a control knot and an Hadamard. So the typical way you do this, they can say, since my Hadamard is only on qubit 0, so I will tensor my Hadamard together with the other identity matrix, meaning that I don't do anything on qubit 2 and 3, right? And then tensor together with the C naught, and then with the last qubit, which is Bob's qubit being idle. So these operations acting on this period states, sort of the tensor products of Alice's original state with the entanglement state, will result me in this form. So you can work on the math saying like I first do the Hadamard on qubit 0, and then I expanded this out into 0 plus 1 divided by square root 2. And then also you perform a C naught operation, which is you're flipping the bits, flipping the second bits if the first bit is 1, right? So after some math, you will obtain this very long, and list of quantum state. Okay, so and then reorganize this sort of A thing together. You can put things into this order. So there's another interesting phenomenon, again, as something to do with the measurements, so which is called projective measurements. The way of projective measurement is that saying if I measure my state into one certain result, the corresponding states will collapse into the state that corresponds to the measurement result. Say if I measure this gigantic areas in here, if I measure the first 2 qubits to be in 0, 0, then my last qubit will be collapsed into alpha 0 plus beta 1. And similarly, if I measure the first 2 qubits as 0, 1, and then my last 2 qubit will be collapsed into alpha 1 plus beta 0 instead of alpha 0 plus beta 1. So similarly, the case also happened with the 1, 0 and 1, 1. Okay, so again, you can sort of observe that the first 2 qubits are the Alice measurement result, right? So Alice information will be collapsed into either 0, 0, 0, 1, 1, 0, or 1, 1. So she can send the information she measured in her operation and send it to Bob. Say if Alice measure 0, 0, then Bob will know that his things is actually alpha 0 plus beta 1. So this, Alice telling Bob that which projection she has made can be sent into this pure classical channel. Okay, so with that in mind, I say if Bob receives 0, 0, Bob now knows that his state is in this form, and then so this is basically the same form as Alice created. So Bob can just don't do anything and then still get the same thing. And then if Bob received 0, 1 from Alice, then Bob knows that the information he received is kind of flipped. So then, like in that case, he will just simply do an X gate to sort of get back to the original alpha 0 plus beta 1. And then, like similarly, if Bob received 1, 0, 1, 1, and he will suddenly know that the information he gets is this, and then he'll just do some corresponding ZX or Z operations to restore the original Alice state. So this is sort of a general outline of what Grover search is. So the goal of Grover search is to find, say, given a large list of n items, and I want to locate one item or multiple items that sort of suit my purpose or suit the criteria I'm looking for. So, say like if you're a computer scientist, like these sort of a big old notation, and then saying like possibly you don't need ON complexity to find to locate that particular omega item under a list of n items, because basically you can just iterate through an array of n size, and then you can just say sort of average times you need n over 2 iterations. In the worst case scenario, you have to iterate through starting from the first location to the end. So you'll need n times. But we by this sort of a smartly crafted quantum algorithms, you can potentially locate these items in O of square root of n times, which is some polynomial speedups over the classical over the classical computer. Okay, so let's try to go things into more details. How do we set up these global search? So one way to set up a database is to say, well, I can set up, say, for a 3-qubit systems, I can have 8 numbers, right, ranging from 00001 until 0101. So you can sort of label them as the 0 state to the 7th state. And then the Grover algorithms use a thing called an oracle, right? So oracle is something that typically in the theoretical computer science sense is a quantum operation that does something as exactly described in here, and usually I'm saying it's usually, but sometimes it's hard to do that. But typically it can be decomposed into a sequence of quantities. So for the purpose of this Grover oracle, what I want to do is that I want the case where for any quantum states, I act on this unitary on that. If my quantum state is not the solution I'm searching for, then I don't do anything. I just keep it the same. And if my quantum state is the thing I'm looking for, I will add a negative phase onto that solution. All right, so X can be any state in the 0 to 7 basis. All right, so for example, let's say if the omega state is the 101, and our oracles will have this corresponding matrix, right? So for all the other quantum states, I will make them the same. And then I will add a -1 phase onto this omega state. It's 101. And then sort of the core idea of global search is we are trying to amplify the amplitude of whatever the state is being flipped, which can be sort of shown in this very nice sort of geometric interpretation. So let's say in the first step is that we're trying to create a xy plane in the sense that the S prime is my original state without any flips or without any amplification, and then the omega state is the final output I wanted, right? So I want to sort of somehow rotate my original state onto the final output we want. Okay, so this is sort of the and for everything we initialize them by puncture pattern marks sequence, and we get a superposition of all of them with the same amplitude. Right, so now my omega state has the same magnitude with others. So if we prefer measurement on this, we have no idea of what the omega is. Right. Okay, so now that's the second step. Now we apply the oracle's reflection to the original state. You can see this oracles will flip my omega state and add a -1 phase onto this. So now after this, we do a thing called a additional reflection, which is something referred to diffuser upwards. So this will translate my state from the -1 phase onto a little bit higher than the other states. Okay, so comparing this and then the original state, you can see that the omega state I want to search is being amplified in here. And then, so this again will be sort of the circuit sequence. And then we're trying to first initialize them by a bunch of paramers into a superposition of all the possible states. And then we repeat the oracles and the diffusers squared over n times. That's saying that I can finally rotate this state to the omega state that I want. And then at this omega n times can be proved in under math. And then in the case where there are multiple solutions, saying that I want to find 2 solutions or 3 or 5 under this array of n size, and roughly it is n divided by n squared, and repeat will suffice. Yeah. So this is the general idea of global search. Now let's go to the actual tutorial to see how we realize this. So let's first again try to go to this thing called global/search that I found in the book. Let's first do some imports. Okay, so let's first look at the 2-qubit case. Say that we have the case where the global search are trying to find the omega equals 1 states under the under the 4-qubit case. Under the 2-qubit case where there are 4 possible states. So now let's set up our global search circuits, which is there are 2 qubits in here. And then I define my initialization by adding a sequence of paramers onto that. So this will be my circuits now. So with the initialization. Now turns on to step 2, which is we're trying to add an oracle that flips the 1 state as I want. So you can sort of notice that for this very simple case, this U omega is simply the CZ gate, right? So the CZ gate is doing the control Z gate is doing exactly the matrix operations as described in here. And then for more general cases where there are 3 or more qubits, and this oracle is going to be a little bit more complicated. But for that case, for 2 qubits, it's simply the CZ operation. So now I have my quantum circuit looks like this after the oracle, and then now turns into step 3, which is the diffuser, right? The diffuser is trying to reflect whatever is being flipped back into the minus state onto the original plane. So in order to complete this, and US equals 2 broad 2 cat s times broad s minus I. This is an identity matrix. We can perform this operation. So first, we know that perform the Hadamard against will bring my S state back to the 0 state, and looks like this. And then then we add a circuit that add a negative phase to the state orthogonal to 0. Right. So meaning that the signs of each state are flipped except for the original 0 state. So this state will becomes this. Now and add this together, and then finally we need to bring back my S state into my original S prime state, which is can be done again by doing the hammer again. So this is my sort of full circuits, and for say. This first part is my initialization, and then this is the oracle, and then the last part is my reflection diffuser. So for this particular case, one can sort of work out the math saying that only one rotation is required to rotate the initial state as to the winner omega state. So we can sort of do these things via simulator. We can see that from the state vector simulator, and at my final state equals the one-line state. And on a custom simulator, I now exactly know that the one-line state is the things I'm looking for. So this is exactly as described that we want to find the omega x11 from a database of n equals 4. Okay. Yeah. And lastly, let me try to maybe just like breeze through a more complicated example of sort of saying in here. So yeah, in this case, we're trying to solve a like a real problem because in the previous case, it's kind of tricky because we kind of know solutions right before we're trying to do the search. Or like are there any things we can do before without knowing the exact solution? So, and in this way, this problem sort of provides a next example. Say, and in this case, we are only incorporating the partial boundary conditions between in each ones, and we can reach the final solutions without knowing it. And yeah, and then so a general idea for Sudoku, I mean for a sort of a simplified binary Sudoku, is that I will have 4 locations which will store either 0 or 1, and then I will try to find a solution where no columns may contain the same value twice, and then no row may contain the same value twice. Say, for instance, if I have a 0 in my V0 position, then my V1 cannot be 0, and my V2 cannot be 0. So, like, this is sort of like a simplified binary version of the original, 9-number ones, right? So, like, some possible solution can be 0, 1, 1, 0, or 1, 0, 0, 1, right? And in this case, I'm not actually telling you the solution, but instead, I'm encoding the boundary condition saying that the nearest neighbors cannot have the same numbers. And then we'll try to evolve through the Grover search and try to find that the corresponding answers that satisfy these boundary conditions. Okay, so since we only have a couple minutes, let me just go over really quick, and then you can go back to the end to look at more details. All right, so this simple circuit in here in line 13 will tells you the parities between the 2 neighboring qubits. Right? Say if both of the qubits are in 0, 0, then these 2 signal won't do anything, so my output will still be 0. But if my the other states are 0, 1 or 1, 0, meaning that they are not neighboring each other. The neighboring ones doesn't have the same number, so then my output qubit will now be 1, right? So 1 means good, and then 0 means bad, because like if it's 1, 1, in this case, both control nodes will give me a 0. Okay, so in this way, we can add all these neighboring information together by these pairs of parity checks. And lastly, we add a multi-control topology, sort of to record if all these information are satisfied. So, and this sort of means that I'm controlling on these 4 bits, and if any bits is 1, so that actually means that all these 4 control bits has to be 1 in order for me to flip the output. If any of them is in 0, which are bad, meaning that the nearest neighbor are having the same number, I don't flip. So this guarantees that all these nearest neighbor conditions are checked. Okay. So and then there's also this complicated process called uncomputing and then via phase kickback. And then this sort of I uncompute my previous result by restoring the previous information for my syllabus, and then thus I can do another iterations by simply repeating the same operation again, and then now I am able to clear up all things in my syllabus. Well, my original bit stayed untouched. So let's take a look at the full algorithm. So define things again. So again, these are the initialization header marks, and to initialize them to all the possible 16 states. And then we do like 2 iterations of this with the diffusers added in the end. So let's define, in this case, okay, define oracle. Sorry about that. Let me do something again. Run things from here. If I set my iterations in 2, and then which is my optimal number of rotations I'll need, I'll finally see that my final output is in here. So this will correspond to my 0, 1, 1, 1, 0 state and the 1, 0, 0, 1. So go back to the original Sudoku plots in here. So this will correspond to say the 0, 1, 1, 0. So that's the state I wanted, and then the other solution is the 1, 0, 0, 1. It's in here. So starting from 0 to 3 in this case. Yeah, and you can sort of change the number of iterations to see how that will happen. And now I put them into the optimal numbers in 2, and then that looks like this. So if I make that iterations equals 1, that means that I'm not rotating the state enough. So in that case, I will see that the other states outputs will be a little bit higher. Right? Something like meaning that this is not really optimal. And then if I change my iteration number equals 3, and this means that I will over-rotate my angles. Now it will look like this. So this means that the solutions is being over-rotated. Okay, so let's bring it back to the 2 rotations. Now back to my optimal solution, which is in here. The other states are all very low, and then the ghost loop states are shown in here.
And this concludes today's session. Thank you very much, and we'll see you tomorrow. Thank you.